Hi everyone. In this video I'm going to demonstrate binary logistic regression using SPSS. Now before we get started I do want to mention a couple of things. First off, I actually have several other videos on this particular topic, but I just felt like it was time to refresh the presentation. So here we are. Secondly, underneath the video description you will find a couple of links. The first link will be to an SPSS data file. That is the data file that I'm working from in this presentation, and you can download that to follow along. The second link is to a PowerPoint that is going to provide a lot more detail that I'm going to be covering in this video presentation. So be sure to download that PowerPoint to learn more about logistic regression in the context of this example. So let's take a quick look at our data set before we begin running analyses. Basically this is simulated data or simulated student data where each row represents a given student. And what we're going to be doing is predicting the probability of a student passing a test as a function of a set of predictor variables. So our dependent variable in our regression model is this pass variable right here. It's a binary variable. It's coded 0 for did not pass a test and 1 for did pass the test. So you can see that all of these students right here, as we kind of scroll down, all of these students did not pass the test, and then you see the ones kind of starting up, and these are all students who did pass the test. So what we're going to do is first run a binary logistic regression where we are going to regress this pass variable onto these three predictors right here, and we're going to treat these as continuous variables. So we have anxiety, mastery goals, and interest. The second analysis that I'm going to run will entail adding in this income level variable to our model, and this income level variable is a categorical variable. It's coded 1 for low income, 2 for medium income, and 3 for high income. So, and I'll show you how that gets added into our model next. So we'll go ahead and begin with our first analysis. We're going to go to Analyze Regression and then go down to Binary Logistic and click on that. We'll move the pass variable up to the dependent variable box, and we'll move anxiety, mastery, and interest over to the covariance box. I'm going to select under Options, confidence interval for the odds ratios, and the Hosmer-Liebeshow goodness of fit test. So we'll click on Continue here. Under the Save button, you can get some additional information that you might find useful. Where it says predicted values, you'll see it says probabilities. And basically by doing that or clicking on that, it's going to generate the predicted probability for each case of falling into the target category or the target outcome category. In this case it's going to be a student who passed the test. So it's the predicted probability of a student passing a test based on their responses to those other predictor variables. And then based on those probabilities we can assign a predicted group membership. So obviously the program is going to do this automatically, and I'll walk you through a little bit of that in a bit. Under Influence, you'll notice that we have these influence diagnostics that are given, and these are useful for identifying cases that may be having a particular undue influence on the overall model, and really don't want individual cases exerting more influence or substantially greater influence than the other cases. So you can use these diagnostic measures here to identify those cases. And I'm not going to spend a whole lot of time unpacking that. I'm going to defer to the PowerPoint where I walk you through some of that with respect to these influence diagnostics. Under the residuals, I'm going to click on Standardize right here. This is useful for identifying potential outliers. And again, I'm going to defer to the PowerPoint to give you more information on the use of that index. So we'll click on Continue and then on OK. And we can now start to look at our output. The first thing you'll notice is we have two blocks. We have block 0 up here and block 1 down here. So block 0, it basically contains information related to an intercept only model, or essentially a null model. So down here where it says variables in the equation, the only I'm going to put in quotation marks variable, if you will, that's included is actually the intercept. So this is where it says constant, we're referring to the intercept. And the reason why this is here is because one of the things that we do with our full model containing our predictors is we compare the fit of that model in relation to this intercept only model. So we'll scroll down and look at block 1, and so this contains our information related to the fit of our full model, basically the model that contains all of our predictors. So the first piece of our output right here gives you an overall test of model fit. So you'll notice it's a chi-square test for our model. The degrees of freedom is equal to the number of predictors, and we have the significance value that's given right here. So we can report that as p less than 0.001. So if this chi-square test is significant, as it appears here, then we would interpret this result to indicate that our full model represents a significant improvement in fit relative to the previous intercept only model. Or you could also state that we would expect that at least one of the population regression slopes is non-zero. So this result that's given here is one indication that we have a good fitting model. You'll notice that the next table says model summary. There are 3 indices that are provided. This index right here, the -2 log likelihood, or you might see it reported as the -2 LL, this is referred to as the model deviance. And so a value of 0, that's actually the lower bound, and that would reflect a perfect fitting model. And then as we move in the positive direction from that, that's reflecting worsening of fit. So the model deviance is, by itself, is not terribly informative. Usually we rely on other indices that are at least incorporate the deviance in their computation, such as the Cox-and-Snell R-square and Nagle-Kirke R-square that's given right here and here. Now, the R-squares, when we refer to that, we're actually talking about pseudo R-squares. So the values that are provided in this table right here are not really designed to be interpreted in the same way as we would interpret R-square in the context of linear regression. In linear regression, the R-square value is interpreted as the proportion of variation in the dependent variable accounted for by the predictors. And again, these are not computed in that same way. It's not using least squares estimation. So we can't interpret them directly, but rather we use the pseudo R-squares as sort of an analogy to the R-square value that we use in the context of linear regression. Now, in linear regression, the theoretical range for R-square is between 0 and 1. The Cox-and-Snell, the upper bound actually will be less than 1. And so that makes it a little bit more tricky when it comes to making sense out of it. The Nagle-Kirke pseudo R-square basically rescales that Cox-and-Snell so that it provides a range between 0 and 1. But I'll be honest, there's just not a whole lot of guidance that I found out there in terms of how to really make sense of these indices, particularly in terms of judging, small, medium, or large pseudo R-square values. So, it might be the case that you might choose to opt not to report on those measures. But nevertheless, we're going to go ahead and proceed on and look now at the Hosmer and Lemishow test. So here, this is another index of overall model fit, or a test of overall model fit. So we have a chi-square test that's given. There's our degrees of freedom and our p-value. Now, unlike the chi-square test that was provided above or discussed previously, here, if it's non-significant, that is actually an indication of at least acceptable model fit. So whereas the previous chi-square test, we were looking for statistical significance as an indication of model fit. Here with this test, non-significance is preferred, as that would be an indication of model fit. So right here we see evidence that our model is at least demonstrating acceptable fit to the data. The next piece of our output, you can see right here we have a classification table. You'll notice that in this output we have the observed outcome and the predicted outcomes based on our model. So with respect to the observed outcomes, you have our two outcomes for the pass variable. We have did not pass the test and pass the test, and the predicted outcomes of basically did not pass the test and pass the test. And so we can look at this particular table to provide further indication of the fit of our model, basically by looking at the percentage of correct classifications based on our model. So looking at our table right here, you'll see with this cell right here and this cell right here, these are representing correspondences between what was observed in the data and what was predicted by the model. So this is basically these are frequencies representing those correspondences. So you'll notice that this first row right here where we have percentage correct, this is essentially calculated as a ratio of the 71 right here to the sum of the frequencies in that row. And that 39.4% is basically indicating that of the 180 individuals who were identified as not passing the test, we had 39.4% correctly predicted by the model to not pass the test. So that is actually referred to as the specificity of the model. In the next row right here, we have the sensitivity for the model that's reflected in this percentage of 80.8. And so basically, this is calculated by taking 198 and dividing it by the sum of the frequencies in this row right here, which is 249. So you can see that among those individuals who passed the test, 80.8% were predicted by the model to pass the test. So that's our sensitivity for the model. So our first row is giving the percentage is giving us the specificity for the model. The second row is giving us the sensitivity for the model when we're talking about the percentage correct. And down here we have the overall classification accuracy of 63.3%. So you can see right here that overall the model's not doing a very good job in terms of predicting the outcome. And what we see is that the model does a better job of predicting who will pass the test than it does in terms of predicting those individuals who did not pass the test. Okay, so next we will transition to the regression table down here. This is our table. You'll notice that we have this column right here. These are our unstandardized regression coefficients. So for these predictors here, anxiety, mastery, and interest, these are the slopes, and then we have the intercept value that's given down here. Now, when it comes to interpreting the regression slopes, it gets really tricky in a certain respect, because basically what we've done when we ran our model is we converted the predicted probabilities of a student passing into a different type of variable called a logit. So if you think about it, basically the predicted probability of y equals 1, which is a student passing, is converted into a new variable that is called a logit, where basically we have y equals 1, or the logit for y equals 1. Now, you may be thinking to yourself, why do I care about this, or why does this matter? And I do actually unpack this a lot more in the PowerPoint, but just briefly, the reason why we are referring to logits here is because when we are trying to model the relationship between our predictors and probabilities, you have to keep in mind that probabilities are bounded at 0 and 1, and that creates an inherently nonlinear relationship between our predictor variables and the probabilities. So what we do is we transform those probabilities into logits so that we can model the linear relationship between our predictors and our outcome. So that's effectively why it matters. So technically speaking, with our first slope right here, if we're looking at anxiety, what this would mean is that as we move from low to high levels on anxiety, the predicted logits, and by extension, the predicted probability of a student falling into the passed category is decreasing. So, and more formally speaking, the coefficient of negative 0.081 would mean that a student who as we exhibit a 1 unit increase on anxiety, the predicted change in logits is minus 0.081, meaning that we have a decrease in the predicted logit of 0.081. With respect to the mastery predictor right here, the regression slope is 0.096, and that basically means that for every 1 unit increase on the mastery variable, there's a predicted increase in the logit of 0.096. And then for the interest variable right here, the 0.042, that would indicate that as with a 1 unit increase on the interest variable, the predicted change in logits is 0.042. So there you go. So obviously that is a very complicated and cumbersome way of talking about this. So just to make life a lot easier, just think about it this way, that basically if your regression slope is a positive value, then what that's signifying is that as you move from low to high on your predictor variable, such as mastery right here, then the predicted probability of a student falling into that target category, being passing the test, is increasing. If we have a negative regression slope, such as with our anxiety variable, then what that would mean that as we move from low to high on the anxiety variable, then the predicted probability of the student passing is actually decreasing. So that's the simplest way to talk about it, because as you can see, it becomes very cumbersome when you're talking about logits. And again, I will defer to the PowerPoint for a much more extensive discussion. We can test each of the regression coefficients for statistical significance. So you can see right here we have our SIG column. So you can see that that anxiety was a significant predictor within the model. You can see that mastery goals was a significant predictor. However, the interest variable was not a significant predictor in the model. Next, if we look at this column right here, these are referred to as odds ratios. And basically, the reason why we are talking about this is because what this provides another way of communicating about the relationship between our predictor variables and the outcome. So think about it this way, that odds are computed as a ratio of probabilities. So in our case, if we talk about the odds that I'll just say y is equal to 1, that is computed as a ratio of the probability that y is equal to 1 over the probability that y is not equal to 1. So I can denote that as 1 minus the probability that y is equal to 1. So the odds ratio is reflecting the multiplicative change in odds per unit increase on the anxiety variable. So formally speaking, you could think about it this way with respect to our anxiety, the odds ratio for the anxiety predictor, that basically for every 1 unit increase on anxiety, the odds of a student passing are changing by a factor of 0.922. And so because that number is less than 1, that would have to mean that the odds are decreasing. With respect to the mastery variable, we have 1.101. So because that value is greater than 1, what that would indicate then is that as we move from low to high on the mastery predictor variable, then the odds of a student passing are increasing. Then for the interest predictor right here, we also have an odds ratio that is greater than 1, signifying then that as we move from low to high on interest, that the odds of passing are increasing as well. So that's basically how you can think about the odds ratio. It's just simply reflecting changes in the odds as we move from sort of low to high on each of our predictor variables. And then with respect to this area right here, this part of our output, we have a confidence interval for the odds ratios. So you can use this if you want to, in addition to reporting the point estimate for the odds ratio, providing an interval estimate for those ratios. And so you could also theoretically, if you wanted to, you could test the odds ratios for statistical significance. And the way that you would do that is assuming an odds ratio of 1 is equal to the null hypothesis, basically meaning that with changes on the predictor variable, there's no systematic changes on the odds. Then if 1 falls between the lower and the upper bound, then we would maintain the null and infer no significant relationship. And if 1 falls outside of the lower and the upper bound, then that would be used to infer statistical significance. So you can see right here for the anxiety variable, 1 falls outside of the lower and the upper bound. So again, that's communicating that anxiety is a significant predictor in the model. 1 falls outside of the lower and the upper bound for the mastery variable, again signifying that mastery is a significant predictor. And then we do see that 1 falls between the lower and the upper bound for the interest variable, which is consistent with our earlier test, indicating that it is not a significant predictor in our model. Okay, so looking at our output, our spreadsheet, remember we had saved a number of values to it. So this column right here, where it says PRE_1, these are the predicted probabilities of a student passing. Remember, that's our target outcome. The reference category is not passing the test. So you'll notice that for the first student in our data set, the predicted probability of passing was 0.29376. So in that particular case, you can see that there was a very low probability of passing, so it's 29%. You can see that this student right here, number 4, the probability of passing was 0.53 or 53%. You can see this student has even a higher probability at about 0.63 or 63%. So it's based off of those probabilities that we can see that we have predicted group memberships. So basically, individuals with a predicted probability of falling into the target group, in this case passing the test, that fall below 0.5, they're going to be predicted to fall into group 0, which is to not pass the test. Those individuals who are predicted, who have a predicted probability that's greater than 0.5, then they're going to be predicted to fall into the pass the test group right here. So you can see these two individuals with predicted probabilities of 0.55564 and 0.53307, both of those students were predicted to pass, whereas these two students, again, were not predicted to pass based on the model. You can see right here we have our Cook's D that we had requested. Basically, these two variables that were created, as well as these right here. These are the influence statistics that we had requested. This Cook's D is basically an indicator of the degree to which a case may be exerting greater influence over the regression results. So you could think about Cook's D as a general measure of the extent of influence of a case on the overall model, whereas these indices right here are the standardized DF betas, and they convey information about the influence of individual cases on the specific regression parameters. So you can see if I highlight over this DFB0_1, that is the DF beta, or the standardized DF beta for the intercept or the constant. And then you can see right here, this is the standardized DF beta for the anxiety predictor, the slope for the anxiety predictor, and then we have this is for the slope of the mastery predictor, and then the slope for the interest predictor. So again, I'm going to defer back to the PowerPoint to give you more information on how to unpack the meanings of those values in the columns. You'll also see right here this ZRE_1. This is just the standardized residual that we had requested, and then this right here is the leverage value that we had requested. Okay, so now let's transition and run our analysis using income level as an additional predictor. And as you can see, this is basically an ordered categorical variable. If we go under the variable view, you can see we have low income coded 1, medium income coded 2, and high income that's coded 3. And so if I go back under data view right here, and I'm going to run the analysis by clicking back on binary logistic, we're going to move the income level variable over to this block right here. And now we need to establish that this is a categorical variable, and we're also going to need to establish a baseline or reference category. So to do that, we're going to go under this categorical button right here and move the income level variable over to this categorical covariates box. And down at the bottom it says contrast, it says indicator, and I'm just going to leave that alone. And where it says reference category, I'm going to select first. Now what happens when we do this, or when we set this up, is that we're going to be recoding this income level variable into a set of binary variables that convey group membership information. So, and the number of dummy variables that we're going to be generating is equal to the number of groups minus 1. So what you're going to find when you run the analysis is that we're going to have 2 dummy variables instead of 3 dummy variables, because the dummy variables are contain all of the information that's necessary to indicate group membership. And so what we'll do is I'm going to click change right here, and now you can see inside the parenthesis it changes to first. So we'll click on continue and then on OK right here. And now let's take a look at our output. So you can see again we have block 0 and the information there is reflecting the intercept only model. Block 1 again is reflecting our full model containing all of our predictors. You can see based on the chi-square test right here, we have statistical significance indicating that our full model represents a significant improvement in fit relative to the null model. You can see that here's our Cox and Snell and Nagelkerke pseudo R-square values that are given. And scrolling down a little bit more, we have the Hosmer and Levasheau test. You can see this is not statistically significant, further indication that we have at least an acceptable fitting model. When we scroll down to our classification table, you're going to see that our sensitivity and specificity for the model are not really that much changed from what we had previously. So the sensitivity for the model is 83.7%. Again, that's just computed by taking the frequency of cases in this cell right here and dividing it by the total frequency for the observed outcome of passing the test. And the specificity, which is 40% right here, is just computed by taking the frequency in this cell and dividing it by the frequencies, the sum of the frequencies in the did not pass observed outcome row. So we still have, again, fairly decent sensitivity for the model, but poor specificity, and the overall classification accuracy is still rather poor. When we look at our regression table below, you'll see that we still have our anxiety, predictor, and mastery and interest. Those are our regression slopes that are given. You can see that anxiety is still negative and statistically significant, indicating that students who are higher on anxiety are less likely or less probable to pass the test. You can see that the mastery coefficient is positive and significant, and that's going to indicate that students who are higher on mastery were more likely to pass the test. And then with the interest variable, you see the slope is positive, but you still see non-significance here. So interest would be deemed as being unrelated to the probability of passing the test. You can see then that we have income level. Now you'll notice right here it says income level and there's no coefficient. That's just kind of highlighting the fact that basically we have this dummy coding system in play, and so there's no coefficient for sort of the low group, if you will. Nevertheless, our dummy variables right here and here have been created automatically by the program. So you'll see for this first one it says income lev, and it's got this 1 right here and income lev 2 right here. And so the slopes for each of these represent the difference between either the medium income level group and the low income level group, or the high income level group versus the low income level group in terms of the predicted probability of passing. So you'll see, for instance, the 0.999 associated with the first dummy variable is indicating, and by the way, it's statistically significant. That's going to indicate then that students who were medium in income were more likely to pass the test than students who were low in income. And then when we look at the next coefficient, we see it's statistically significant, and that's indicating that students who were high in income were more likely to pass the test than students who were low in income. So again, what we've done is we've taken our categorical variable, and through SPSS, the menu, we can effectively generate our regression output where the program does the dummy coding for us. Otherwise, we would have to manually do that dummy coding. Okay, so that pretty much rounds out this video presentation. Again, I encourage you to download a copy of that PowerPoint. I just kind of blew through all of this rather quickly, even though 30 minutes is still a pretty long time. But nevertheless, there's a much more information in that PowerPoint that you probably will find valuable. So thanks for watching, and y'all have a good day.